Chapter 8, Estimating Single Population Parameters. In this video, you'll learn about point estimates and confidence interval estimates for a single population mean. Recall in previous chapters where we learned about sample means and sample proportions. These are known as point estimates, in that we are using the sample data to estimate what's going on in the population. So here are some familiar symbols that we've seen consistently over the past several chapters. We have mu for the population mean and x bar for the sample mean. We have lowercase p for the population proportion and p bar for the sample proportion. So we already know these symbols. Recall in Chapter 7 that we learned about sampling error, in that our statistic from a sample is subject to sampling error because it's not a perfect representation of our population and its parameters. So that concept is carried into Chapter 8 as well. In this chapter, we're going to build on our point estimate by developing a confidence interval estimate that goes around it. An interval is the distance between two numbers. So for instance, an interval for the time it takes me to drive to work could be between 35 and 45 minutes. Or perhaps another interval could be the age of students in our class is between 18 to 30 years of age. These intervals are based on a particular confidence level. A confidence interval estimate, then, is the interval developed from a statistical sample, such that if all possible intervals of a given width were constructed, a percentage of these intervals, known as the confidence level, would include the true population parameter. So we can see in the very middle is our point estimate from our sample. Say my average commute time from a sample of 5 days that I drive to work is 40 minutes. So my 40 minutes goes right here. Then my lower confidence limit is 35 minutes and my upper confidence limit is 45 minutes. Note that the distance from my sample mean to my lower and upper limits are the same. But how do we know what our lower and upper limits are? The format of our confidence interval estimate is therefore the point estimate plus or minus the critical value times our standard error. We've worked with these three pieces before. We're simply putting them together in order to create our confidence interval estimate. So our point estimate is our sample mean. You already know how to calculate this by hand and with Excel. Recall the equals average formula. We also learned about the standard error in Chapter 7, which is the standard deviation divided by the square root of our sample size n. The critical value is the z-values that we previously used Excel to find the probabilities of. We're now linking these confidence levels, in terms of percentages, to their corresponding z-values. Here is a table with the most commonly used confidence levels and their z-values. I'll show you how to find them in Excel, but since these are the most commonly used ones, this is a quick reference table when we're asked for a particular confidence level with its corresponding z-value. Let me explain a bit further how we get these z-values with confidence levels. Recall when we converted an x value into a z-value and then used Excel, it would give us the area from the middle out to a particular z-value. So for instance, the z-value of 1.96 gives us 95% of our data. This is nearly 2 standard deviations on either side of our curve. What our 95% confidence interval tells us then is that 95% of our confidence intervals will fall within this shaded area. Let's see some examples. In this first example, where I have a particular sample mean and my interval is a particular width, the true population mean will fall somewhere within this interval. In my second sample mean, my point estimate is so far over to the left here that we can see that our interval does not include the true population mean. So it's outside of our 95% confidence interval. In our third sample mean, my point estimate falls in this shaded region, and therefore the true population mean is captured within this interval. Same with our fourth sample. And we can keep repeating this over and over and over with different sample means. And we'll find that 95% of them will include the true population mean, while 5% will be outside in the two tails combined. Hence, you see the 0.025 on either side, because when we add 0.025 to 0.025, we get 0.05 or 5%. So you can see how the 95% and the 5% complement each other. Because recall that in our distribution, all our probabilities have to add up to 100% or 1. Let's look at our example. The distribution of hours worked by students at MiraCosta College is normally distributed, so we know it's bell-shaped. If the population standard deviation is known to be 5 hours, construct and interpret a 90% confidence interval estimate for the mean hours worked by all students if a random sample of 64 students has a mean equal to 23 hours. So we'll plug in our numbers from the story. Our point estimate given to us is the sample mean of 23 hours. Our critical z-value is based on our 90% confidence interval estimate desired. So I go to my commonly used confidence levels, and I can see that at 90%, that's our z critical value of 1.645. And then our population standard deviation is given to us at 5 hours, and our sample size is given to us at 64. So I'll go ahead and plug in our variables into our formula. So I want to solve for everything to the right of my plus or minus sign. That will give me 23 plus or minus 1.03 rounded. Then to get my confidence interval estimate, I will subtract the 1.03 from my sample mean to get the lower confidence limit of 21.97 hours, and I'll add the 1.03 to my sample mean of 23 hours to get the upper limit of 24.03 hours. My sample mean is in the middle of my interval, and the 21.97 hours and 24.03 hours are on either side of the interval. So based on our sample data, with 90% confidence, we can conclude that the true population mean is somewhere between 21.97 and 24.03 hours. In other words, because we are using a sample to estimate the true population mean, we wouldn't tell a decision maker an exact value. Instead, we would give them an estimate, because we know that our point estimates are prone to sampling error, and we have to account for this. Now, on the right side of our plus or minus sign, where we took the critical z-value times our standard error, this is also known as the margin of error. You may have heard of this term before, like with election polls where pollsters will estimate how many people will vote for a candidate plus or minus the margin of error. The margin of error, as you can see in our visualization here, is half of that interval, from the middle to the limit. In other words, the margin of error indicates that the sample mean of 23 hours is within 1.03 hours of the true population mean. Now, what happens if we modify our confidence level? Keeping our sample mean of 23 hours the same, and our standard deviation of 5 and the sample size of 64 students the same, the only thing I'm changing is the confidence level, which requires a different critical z-value. So using my calculator, I will get different margins of error. As my confidence level increases, so does my margin of error, because I'm making my interval wider. What happens if we modify our sample size? Here we are keeping our sample mean of 23 hours the same, and our 90% confidence interval with its critical z-value of 1.645 the same, but we're changing our sample size from 64 to 100 and 144. You'll notice that our margin of error now gets smaller. Recall when we learned about the central limit theorem? The bigger the sample, the closer we get to our true population mean, and our curve becomes more narrow. So some things to note. We are going to have some conflicting objectives as a decision maker. We want a small margin of error, meaning we want to be as close to the true population mean as possible. That allows us to make better decisions. But we also want a high confidence, because 99% is better than 80%, which means more of our intervals or our data falls within that shaded area. And at the same time, we want a smaller sample size because in business, we have limited resources in terms of time and money to be collecting sample data. So we need to find the right balance between these three things. So some things to note when using Excel. In Excel, it asks for an alpha, which is denoted by this Greek letter A. And alpha simply means you're going to take 1 minus your confidence level. So for instance, if we're working with a 95% confidence level, we would do 1 minus our 95% or our 0.95, and that'll give us our alpha of 0.05. To find a critical z-value, I would recommend using that reference table I gave you, but if you want to try it out in Excel, or if you're asked for a percentage that's not in that commonly used table, say like 96%, then you would use this formula here. Note that this ABS means absolute value, so that when we get our critical value z, it's positive. If you forget to do that, it's just a negative critical value. You just want to ignore that negative. So for instance, if I want to know the z value for 95%, I would type in this formula. My alpha that we found here is 0.05. I will divide by 2 because I've got the two tails on either side of my curve, and that'll give me the z value of 1.96. But as you saw, this was in the table. So if you want to reference the table, it is probably faster than using Excel. So for our margin of error, rather than doing it by hand, that right side of our plus or minus sign, you can use this formula here, equals confidence.norm, where you'll enter your alpha, the standard deviation given to you, and our sample size. So for instance, I would type in this formula, plug in my values, and I would get a particular margin of error. So using your worksheet, problem 3, which is also our homework problem, construct a 95% confidence interval estimate for the population mean given the following values. We have a sample mean of 300, a population standard deviation of 55, and a sample mean of 250. I've also put our handy commonly used confidence levels and their critical values of z, so you don't have to necessarily use Excel if you don't want to. So step 1, what's your sample size? So I make sure I know my sample size is our little n, that's 250. The desired confidence level in the problem states 95%. You're going to compute, if asked to, or find the sample mean in the story. So it's just given to you here at 300. And for our critical value, to get the z value, at 95%, I could read my table and it tells me it's 1.96. I do put the formula here for convenience if you want to try it in Excel. And then for step 5, to compute our confidence interval estimate, I'll show you how to plug it in. So if you want, you could do it with your calculator, and then I'll show you how to do it in Excel. So I'll take our variables known and go ahead and plug it into the formula. And then I can solve our margin of error here on the right using a calculator. So I would get 6.82. And then to get our confidence interval estimate, I will subtract 6.82 from 300 and add 6.82 to 300 to get my lower and upper limits. Now, if you'd rather use Excel to get that margin of error of 6.82, you can type in this formula here. So let's see how this looks like in Excel. So here we have our problem, and to the left here is when we're finding the margin of error when the population standard deviation is known. So I'm going to use this formula right here. And as a reminder, I put the symbol here for our margin of error. So I'll type in equals confidence.norm, parentheses. Our alpha is 0.05 because 95% was our confidence level. And so I put the reminder here that alpha is just 1 minus that confidence level. And then our standard deviation is given to us at 55, and our size or sample size is 250. I'll close my parentheses and hit enter, and that gives me my 6.82 margin of error. So then if I want to find the lower and upper limits, I would take equals my sample size of 300 minus our 6.82, the margin of error. That'll give me my lower limit of 293.18. And then taking my sample size of 300 again, I'll add our 6.82 margin of error, and that'll give me my upper limit of 306.82. So you can see those are my lower and upper limits.